All right, welcome everybody to the second to last day of fluids. We're going to start today by watching a little bit of a video. If you're in heat transfer and have done the homework, I apologize, this is probably like the fourth time you've watched this portion of the video, so just feel free to zone out for like 5 minutes. But before we start talking about boundary layers, I want to make sure we at least have a little bit of context or a refresher, if nothing else, of some of the basics of what's happening. For the last 2 days here, basically what we're going to do is try to, we'll kind of rediscuss some stuff that we've talked about already, but also kind of use this as a chance. David, can you mute your mic? Thank you. All right, so we'll also use this as a chance, as kind of like a grab bag of maybe some interesting things, kind of like the last homework assignment, some interesting things that you may run across that we didn't have time to really go into any detail on. So we're going to talk a little bit today about external flow over top of objects. We've discussed this briefly in the context of like drag force and similarity. We also talked about or watched some videos showing some kind of weird effects for drag force on different objects. So we're going to start to try to unpack. Today we'll unpack drag force a little bit more. Again, not going into really much depth, but just trying to scratch the surface because there's a lot like we could do on drag force. And then we'll, on Friday, probably wrap up the discussion of drag force and talk a little bit about some other stuff and some of the exam stuff. But we'll start today. We'll watch this video. For those of you online, if the sound is bad, I just posted the link in the chat. We're going to watch about the first 6 minutes of it. So we'll get started. Again, if this is your fourth time watching it, I apologize. Just enjoy the inside of your eyelids for a couple of minutes.
This drawing, derived from potential flow theory, shows how the streamlines around the combination of a flat plate and a cylinder would look if fluids did not have viscosity.
So this is operating like under Bernoulli's assumptions, or the
fluid, water,
no viscosity.
Goes around the same shape. The flow is quite different. Boundary layers, thin layers of fluid in which viscosity affects the flow dynamic, are formed along the surfaces of the objects. Behavior of these boundary layers under the influence of pressure gradients can, in some cases, drastically alter the flow. This streamline pattern is very nearly what one would predict from liquid flow theory. Because the Reynolds number is large, influences of viscosity are confined to a narrow region close to the surface of the wing. The primary effect of viscosity is simply to create a drag force on the wing through the integrated effect of surface shear stress. As the angle of attack is increased, viscous effects become more pronounced. Pressure gradients imposed on the boundary layers become more severe, and separation occurs on the upper surface. Now the airfoil is stalled. A region of recirculating flow is formed over the upper surface of the wing. In order to understand how viscous forces can influence the entire flow field, we shall look at what causes boundary layers, how they grow, how they respond to pressure gradients, and the difference in behavior of laminar and turbulent layers. Before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone. These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timeline, the vertical patches of bubbles, remain perpendicular to the streamline shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected. The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth. The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer. The thickness of a boundary layer is sometimes defined as the distance delta from the surface to where the velocity u reaches some fixed percentage of the free stream value. For our purpose, we will use 95% of the free stream velocity to define the thickness of our boundary layer. The gradient of the velocity normal to the wall, delta u by delta y, times the viscosity mu is the wall skin friction or shear stress tau. The greater the velocity gradient normal to the wall, the greater the shear stress. Thickness along the plate.
Okay, so then we'll go on to discuss a bunch of other things. You've watched bits and pieces of this before. Maybe you've watched the whole thing before. But hopefully this gives us a feel for a little bit of what we're going to be discussing with boundary layers and just kind of a refresher for some of the basic physics of what's going on. Right, we have these velocity gradients at the wall are really what's giving us friction. That's giving us shear stress or skin friction. But that's not all that's going on in these systems. So I'm going to take a little bit. We're going to switch over from video to notes. It's going to take me a second. So just bear with me. If you want to get out a page of notes. Got to switch over computers here. Where are we? Okay, you guys can't see it. No, I'm not plugged in. All right, we'll get there. Can you see me? Not yet. Okay, cool. All right, so if you brought multiple colors today, it's going to be a bonus, because I think we're going to try to draw out some pictures. Again, we're not going to go into all of the detail, but I just want to sketch out some of the basic physics of what's going to be going on. So this is covered in more detail in chapter 9. Again, we're kind of going over all of chapter 9 in like a class in a little bit, so we're not going into a whole bunch of detail. But this is external flow. All right. So what are some of the kind of key concepts and ideas of external flow? A lot of what we're thinking about, we're talking about fluid flowing over some solid object. In a lot of cases, we're interested in the drag force on that solid object. You know, whether we're talking about a baseball or a car or whatever, a lot of times we're interested in the drag force, or what force the fluid is exerting on that solid object. So to understand that, we have to think a little bit first about what's happening at the surface of the object. And that's where the stuff we just looked at on boundary layers comes in. So if we, again, just picture the surface of an object, we'll call it a flat plate, but a lot of this stuff will translate between flat plates and other shapes. We have some velocity coming in here. Right? If you're in heat transfer right now, we've drawn pictures like this a lot. So hopefully a lot of this is refresher. Then we would have the growth of a boundary layer. We watched do that like half of the way along your plate, not the whole way. So this is our boundary layer. And if we look at the fluid inside of that boundary layer, right, it's going to maybe look something like this, right? It's going to still be the same velocity far away because we haven't ever felt the effects of the surface. And then we're going to slope down to 0 velocity because of the no slip condition. So far away, nothing's happened, but close to the surface, we felt the change at the surface, velocity 0, no slip condition. Right? We just watched this experimentally. At some point along the surface, right, as this continues to grow, at some point we're going to hit a transition point. Again, we've seen this in flow inside of a pipe. We are laminar in some region, and then as the velocity goes up, or as the diameter of the pipe goes up, or whatever, we flip to turbulent. Same thing for flow along the plate. We're going to be laminar for some region, and then we'll flip to turbulent flow. We didn't see that in the experiment that we just did. We still have a boundary layer, but now the physics kind of changes, because now we have mixing going on. So in this, we have a much more kind of blunt velocity profile. We'll talk a little bit about why that is, but we have these kind of two regions. We have over here our laminar boundary layer, and on this side we have a turbulent. We'll abbreviate it as BL. So these are kind of two separate regimes that we're going to think about. The physics that's happening in each is a little bit different. But before we dive into that, let's just start with a definition. So what do I mean when I say boundary layer? So a boundary layer is just the area near a surface where velocity is decreased / changed. Relative to the free stream. So it's the area that we've felt the effects of there being a surface there. Just as an example, right, next time, it's not super windy today, but it's a little bit windy. When you walk outside after class, watch the grass. On a windy day, right? Go outside, look up at the trees. The trees are blowing around, look down at the grass. It's perfectly stationary and not moving at all. Or if it's super windy, maybe it's like just flickering a little bit. Why is that? Because it's in the boundary layer. It's near the ground. The ground is the no slip condition, so the air at the ground is not moving. Right? Okay, so you can still, like, the wind can pick things up off the ground because of shear stress. So if you see like the wind blowing over sand, it'll pick up the sand and move it because there is shear stress there. So that shear stress can pick up things and move it, but the velocity at the ground is 0. So if you look at the grass, doesn't really do anything. Right, we all live inside of the boundary layer for the wind. That's why if you go like up above the trees and buildings and stuff, you get out of the boundary layer and all of a sudden the wind is stronger because we were inside of this region where velocities changed. But that's a boundary layer. It's this area where we've kind of felt the effects of the surface. There are some key differences in the fundamental physics of what's happening in a laminar versus a turbulent boundary layer, though. So let's just kind of make a table of some of the comparisons between these two. So in a laminar, and a turbulent boundary layer. So in a laminar boundary layer, the flow is, or the velocity is really dictated by momentum diffusion. So momentum transfer is by diffusion. Okay, what do I mean by that? Really, it's governed by this value nu, or the kinematic viscosity. Okay. Again, what do I mean by that? So like the fast, well, really the viscosity really drives the physics. So what's happening, right? The no slip condition is saying the fluid at the surface is stopped, and viscosity is like dragging on the fluid layers above that and slowing it down. Right? So viscosity is what's causing the boundary layer to grow. It's the fluid layers, the slow fluid layers, kind of pulling on the fast fluid layers and stopping them. So that's what's really governing the physics, is this is viscosity. We have black. So viscosity is really kind of driving the physics. That's driving momentum transfer, momentum diffusion, the changes in velocity. We also have relatively low shears. Okay, what do I mean by that? Right. So the shear stress is du dy. So this is the slope is relatively low. If you want to see that, like, look at the image that we drew above. Right, so what are we talking about? We're talking about the slope here at this surface. That slope is relatively low. When we have a laminar boundary layer, when we have a turbulent boundary layer, as we'll see in a second, that slope is much steeper. Right, we go from 0 to fast really quick. In a turbulent boundary layer, we go from 0 to fast pretty slow. It's kind of a gradual change. In the laminar boundary layer, which means that we have relatively low shear forces in that boundary layer. So we have kind of low skin friction. Okay, which again should kind of jive with your idea of friction and skin friction for flow inside of a pipe. That's what we've mostly dealt with. Laminar flow is low friction, turbulent flow is high friction. We're going to see the same effects here. Laminar flow, that's going to be generally lower friction at surfaces than turbulent flow is. Okay, so laminar flow, it's really a viscosity is kind of driving the physics. Turbulent flow, we have really the momentum fluctuations, the turbulence, the mixing, the physical mixing, that's driving the physics of what's happening. So we have momentum transfer by turbulence, right? So it's by like physical mixing. The velocity fluctuations that are really driving momentum transfer. So what I mean is, like, the slow fluid at the surface, the fluid that's gotten really slow, gets physically mixed up and like thrown into the fast moving fluid. So you're getting fast fluid going down to the surface and slow fluid at the surface going up into the fast, and you're physically mixing things around. You're not relying on viscosity to do the work. It's the physical mixing process that's doing the work, just like it is in pipe flow. That's why we got in laminar flow, we would get kind of like a parabolic shaped velocity profile because viscosity is doing the work. But in turbulent pipe flow, we got kind of a flat nosed velocity profile because this turbulent mixing was doing the work. So we get the same general effects in flow over top of an object that we had in flow inside something. So a lot of the kind of thoughts and intuition that you have of laminar versus turbulent in a pipe, same type of stuff applies on the outside of an object. So this also means that we have relatively high shear, right? Tau yx is mu uy, so this slope is big. So these are, turbulent flow is going to be high skin friction. And one of the key insights is basically all of the things that mattered for flow inside of a pipe are going to matter in similar ways to flow outside of an object. So skin friction is very, well, let's not write it there. Let's jump out and write, okay, so yeah, so laminar flow, turbulent flow in a boundary layer, it's broadly the same types of things that you know for flow inside of an object, right? It's the same type of physics, same kinds of things happening. One of the differences, though, is in external flow, a lot of times we're interested in drag force. And drag force can give us some kind of interesting effects. So we saw a couple videos where some examples of drag force on objects where like you made a ball a little bit rough and it behaves really differently. We saw it with some of the soccer ball videos that we watched last class, where like slight changes to the seam length and surface roughness of the ball made it so that, you know, the people playing soccer with it said that that one kicks totally different. So if we want to look at external flow, a lot of times we're interested in drag force, and the difference is there are kind of two competing, often competing things that are at play, two competing effects. So in external flow, we have two types of drag. We have two distinct reasons why we might have drag force on an object, right? A force resisting the movement of that object. Thing one is, I think, the easiest one to grasp and the one that we already have a fairly good knowledge and intuition of the things that would matter. That's skin friction. Okay, so skin friction, really here the same ideas apply as friction in pipe flow. Okay, so what do I mean by that? Right, skin friction is basically the same, again, it's not the same number, but the same processes, the same ideas as head loss in pipes. So we get effects like, right, laminar flow has lower head loss. So laminar flow has lower skin friction. Rough surfaces have higher friction coefficients and flow in a pipe, so they have more head loss. Rough object has more skin friction. So rough object has generally more skin friction. Laminar flow has less skin friction than turbulent. Okay, so again, I think hopefully you feel like it jives with what your ideas and your intuition for pipe flow is. What are the factors that cause it? Right, we're going to get higher friction with higher Reynolds numbers, like all of the same kinds of things that you would assume with pipe flow, you can assume with skin friction. The one that's harder to deal with is, and the one that can be more counterintuitive more often, is the second one, which is pressure drag. Okay, pressure drag is the one where weird things happen. Skin friction kind of behaves as we think it should, right? It's easy, well behaved. Pressure drag is weird and is the cause of weird things in external flow. It's a cause of all of the systems that we looked at, like we watched the video with 3 different systems that all behaved a little bit different than what we expected. All of those weird behaviors were in some measure because of pressure drag. So the pressure drag is caused by pressure differences pressure differences between front and back of an object. Okay, so what we can have sometimes when a fluid flows around an object, we can get pressure build up on one side and low pressure on the other side, and that causes a net force on the object, which is what we call pressure drag. Right? We already know like pressures can apply forces to objects. The force is the pressure times the area. So if we have a big force on one side and a small force on the other side, there's a net force on the object. So let's look a little bit at what causes that. So we'll first look at kind of the, if there's no viscosity, what happens picture. So this is the no viscosity picture. So this doesn't actually happen because it's no viscosity. But if we had no viscosity, what would happen, for example, if we had a ball? Okay, what would happen, we would have a fluid flowing up against the ball. It's going to come in here and come to a stop at the front edge of the ball. So this is our stagnation. Stagnation point. And we're going to get a change, right? As the fluid slows down and comes to a stop, we always have this trade-off between velocity and pressure. So as velocity goes down, pressure goes up. So our pressure here is equal to pressure plus 1/2 rho v squared. That's our stagnation pressure. And if we did like Bernoulli's equation kind of thing, as pressure goes down, velocity goes up. As pressure goes up, velocity goes down. So these things are always in balance because energy is conserved. So that's what's happening. We have this buildup of pressure on the front edge of the ball, where the pressure is higher than, say, atmospheric pressure. If we watch what happens with some of the fluid that goes actually around the object, it's going to be coming in here and curve and go up and around. At the top here and at the bottom, so at the two poles of our object, we're going to have the highest velocity. So this is our highest velocity, so our lowest pressure. So we have the lowest pressure at that pole. And then what would happen again as this guy comes around, I'm going to try to draw this okay. He's going to come, and that was really bad. Let me try again. Okay, so this is coming in here, goes up and around and comes back there. Okay, maybe you can do better than I, but you at least get the picture. So what we would have happening here, we would have low pressure at the top and bottom of our object. We have high pressure on the front edge, but we also have a stagnation point here. So the fluid flows totally around the object, and we get high pressure on the front side, and we have high pressure on the back side. So the pressure forces cancel out, and we don't have any pressure drag. So in this case, we have, I'll draw it in black. So we have high pressure on the front and back side of our ball. Which leads to no pressure drag. So if the fluid can follow and kind of follow around the whole object, we do get high pressure on the front side of the object, but we also have high pressure on the back side of the object. So the only thing that matters then is skin friction. We don't have any pressure drag. There's no pressure difference between the front and back. What happens in a real object, this is a no viscosity picture. In a real object, we've talked a little bit about this in the context of minor losses, and we watched some videos on this. But if we zoom in just at what's happening at the top of the ball, so we have this is our ball here. We have right up the center of that, this is our lowest pressure. And right over here we have high pressure, and here we have high pressure. But right at that line we have our lowest pressure, high pressure on each side. If we imagine what's happening to our fluid as it is going around the curve of this shape, there's a distinct change right as you get around that top part, right? As we're coming up on the left side, as we're going up to that tops part, we have, again, so this is that's our boundary layer. If we look at our fluid, it's going to look like this. Our fluid is going that way. We have here high pressure pushing on the backside of our object. And we have, I'm dramatizing this, but we have low pressure pushing on the front side of the object, right? So here at the back, we have a big arrow. Here at the front, we have a little arrow. So in this region of our flow, pressure helps to push along the flow. Okay, so that's kind of the key insight, is we're going from high pressure to low pressure, so pressure is pushing everything along, it's keeping things moving. When we get across that vertical line, when we cross that boundary, things flip. So if we go over to this side, get my blue again, the situation exactly flips. So at this point in the flow, we have now, right, here's our fluid, but now we have a high pressure here at the front. And only low pressure here at the back. Okay, so what is the effect of that? Right, the effect is eventually, we watched this happen in one of the videos, right, that's going to cause the fluid to slow down. And where the fluid is moving fast, inertia is enough to keep it moving. It just slows down. But where the fluid is moving slow, it slows down and can come to a stop and actually turn around and start going the other way. So we can look at what would happen is eventually we get to a point here where our flow looks like this. Where we still have like relatively low pressure pushing on in the front and high pressure are pushing on the back. And at this point, we have the flow separates from our object. Again, we watched a video that we watched this happen under a couple different conditions. You can think about it. So what's happening in this case, if you think about it kind of like a force balance type case, we have a net force from pressure pushing to the left. We have a net force from viscosity trying to drag things to the right. It just so happens that pressure is winning. So we have, if you think of it again from like a momentum picture, viscosity is kind of trying to, right? So viscosity is trying to diffuse momentum down into that slow moving fluid. It's just not fast enough. So we get this flow separation. So if we, again, look at what happens with our object, our real picture is not this. Our real picture of what happens is that our flow separates and we see a wake. And this terminology, flow separation, is broadly used in fluid mechanics. And you maybe have heard it in some of the videos that we've watched. So what effectively happens, we have our object here, our ball. We still have on the front side of the object, things kind of behave as we maybe would expect. We still have our stagnation point where P equals P plus 1/2 rho V squared. So that all behaves as we think it should. But what happens is the fluid just above there is going to go up and it's going to get to the poles and it's not going to be able to follow the curve of that shape. It's going to just keep moving straight on its merry way. And the fluid at the bottom is going to do the same thing. It's going to get to the poles and it's fine, and then it's going to be moving straight along its merry way. So we get what develops here is a wake behind the object. And we're all obviously familiar with wakes forming behind objects. Right? We've visually seen that happen. The reason that happens is because the fluid is not able to follow that curve of the object. And it's because of this difference in pressure, because right at the kind of the pole of the object, that's where we have lowest pressure. And as that curves around, pressure starts going up. And that causes this flow to separate from the object. Functionally, what happens is this wake leads to high pressure at the left / front, the left in my picture, and low pressure at the right/back of the object. Okay, so when this wake forms, we get a high pressure on one side and we get a low pressure on the other side, which causes a net force, right? Pressure is, force is pressure times area. So you get a big force on the front and a little force on the back. So you get a net drag on the object. So the take home, and we'll end here. We'll talk a little bit more about this next time. But if we can stop or delay boundary layer separation, we can reduce pressure drag. Okay, so the take home is once the boundary layer kind of comes off of the surface of the object, it creates this wake, this area of low pressure behind it. So if there are things that we can do to either stop that from happening or make it so that it doesn't happen as much, or it happens like further along the curve of the object, those are things that are going to reduce the wake and reduce the pressure drag of our object. So we'll look a little bit at that next time. In the couple minutes that we have left, I wanted to, because this is everybody's favorite thing, I wanted to draw your attention to some exam stuff, because obviously our exam is coming up. So I made we'll talk more about this next time, on Friday, but just in case you want to play around with stuff before then, if you're feeling in a mood where you have lots of free time on your hands, as I know we all do right now. There's some stuff on the format of the exam. The exam is going to be, the first part of the exam is going to be 4 different FE style questions, fundamentals of engineering questions. So you may think I haven't seen those before, but you have. We've been doing them in homework, we've been doing them in exams and quizzes, and like we've seen these before. So they're not going to be wildly different than problems that you've seen. The difference is they're going to be multiple choice. Whereas when we've done them in class or in homework in the quiz, we've done them as like short answer problems. So they'll be the same thing, just multiple choice. So I point to a couple specific places in there where we've seen these problems before, if you want to like check back and say, oh yeah, that's the type of problem. It's obviously going to be problems on the real FE exam. There are problems that we didn't really cover. I'm not going to give you any of those. They're going to be things that we've covered. It's going to be the same topics, the same material, just so that you have a little bit of familiarity if you do end up going on to take the FE exam, with a little bit what that format is like and how to handle it before you dive into the real thing. The biggest difference for the FE section of the exam is what you get for notes. So there's this FE supplied reference materials. You click on that. There are like 11 pages of equations and definitions and some examples. And these are, for the FE portion, these are the only notes that you will get. So you'll not get your own personal handwritten notes, again, to make it feel a little bit like what the FE exam is, kind of like a practice for the real FE exam. So spend a little bit of time looking through this just to kind of familiarize yourself. It's not a bad idea to like use this to help you make your own notes and study guide. You're certainly welcome to do that. But there's a lot of good stuff here. There's stuff that we didn't do here. I'm not going to expect you to know that and be able to use it. The FE stuff will be stuff that we've done in class. Then, so we'll do the FE part. You'll turn it in and then get the rest of the exam. The rest of the exam will be similar types problems to what we've done on previous exams and quizzes. I made 2 other things. I made a study outline just so you can kind of remind yourself what we've actually covered and done. I've split it up kind of by chapter. We didn't go through all of the stuff in every chapter, so I've kind of highlighted what I think are some of the highlights from everything. So you can go through and remind yourself, okay, yeah, I know what that is. I know what that is. I have no idea what this is. Let me go and figure out what I'm supposed to be doing for that. So hopefully this helps you as you start to try to piece together what we've been talking about. And then what I think is probably for both the FE part and for the exam part, what will be the best study guide. I made a list of a bunch of questions from all different parts of our book. Just kind of trying to draw out what are the key topics or key ideas from different areas. So I have a whole bunch of different problems, some example problems for what might be a short answer question or some examples. And then this obviously also has solutions to it. So there are a lot of problems there. I don't recommend going and solving all of those because that's a lot. But you can use it to at least like look through the problem, make sure, yeah, I know how I would solve this. I know how I would solve this one. I have no idea for this one. Let me go look at the solution. So you don't need to solve all of those, but hopefully they can be, you can use those as a useful way to gauge whether you feel like you have a good handle on that material. So we'll talk more on Friday about the exam because we're already 2 minutes over. But have a good Wednesday. Finish up strong. We'll see you back here on Friday for the last class.